slide, but today I will be walking you through a bit of 4 different material types and 4 different applications. And in all of them, I'm going to argue that plant-based polysaccharides can bring unexpected benefits. And as already was said in the very beginning of the seminar today, often we credit these materials for bringing the advantage of sustainability that is related to the inherent renewability of these materials, as well as the possibility to source them from bio-waste, especially now that we are moving more towards circular economy type of thinking. Also, these materials are inherently abundant. They are biosynthesized all the time in the nature in large scale, as well as there is the unfortunate truth that all the time there is a lot of bio-waste produced and it's burned in energy production or just simply tossed away in large scale. And I'm going to argue that we need to do something for this. Also, the third great aspect of these materials is that they provide a carbon sink. So if you think about functional materials that would last decades, so it's also a great opportunity to bind some carbon into them. And thus the question that my research group is asking is, how can we bind waste carbon into these materials? And the final thing that I'm going to argue today is about how, by using these plant-based materials, can we actually, in addition to all the sustainability aspects, can we actually add an extra perk or an extra functionality that is inherent to these materials? All right, so let's move forward. So today I will walk you through the green transition that is hopefully slowly going on. First of all, in tunable photonic films. So here you can see this type of transparent cellulose acetate film on top of a leak. Then I'm going to argue that these materials can make a great difference when we are trying to build flexible electronics, and especially more durable flexible electronics. Then few words about construction industry and how plant-based polysaccharides can help us in building green transition in construction industry in form of lightweight acoustic insulator materials. And then finally, I will have few words about environmentally responsive textiles that can react to heat or light and how we can maybe make them a bit more sustainable. All right, so let's start from tunable optics and tunable photonic films. So here, in addition of sustainability, we believe that these materials can help in building flexible films and also more tunable optics into these films. And once my group started to move towards this field, so we started from this big review article project where we were looking into lignocellulosic materials and how, if we change the source of the material or the film making method, how we can produce different type of optical functionalities into these films. So here are some examples of thin films made out of lignocellulosics, and here is sort of pictures of all the possible optical functionalities that these films can produce. And I think this is quite wonderful that depending on how the material is structured, we can get either just like this type of reflective gratings or structural color or just like bright white opaque films. But the thing that my group has been especially interested in is this type of translucent films. So the idea here is that most of the light would go through the film, but it would go towards diffusive transmittance. So it doesn't go directly through, but it scatters a bit and then scatters more. And that's what we call haze. And one of the interests why we are looking into this is that this can be used as light guiding layers in photonic devices. So if you think about photonic devices, especially of thin film devices, so often there would be the interest of trying to make as much light captured as possible. And how can this be done if we add this type of light management layer on top of it? So if we optimize the engineering of this type of layers, so we can then aim for, first of all, high transmittance at the critical wavelengths, Then secondly, low reflectance at the surface so that we can capture as many photons as possible. And then finally, high haze or high diffusive transmittance, because if we have then a thin film device that is placed just below of these light management layers, so then if we can diffusively transmit the light, then we can actually decrease the thickness of this photonic device below the film, since the optical path length of the light will be increased thanks to the film. So this is a concept that we are highly working on, and what we have also figured out in collaboration with RISE and with their excellent different degrees of CNFs is that what type of CNF or CNC or other lignocellulosics you use for building your film, it really has a big impact on the diffusive transmittant properties that the film will have. Then I want to introduce a concept again for diffusively transmittant films, which is now a bit different, and we've been developing it in my lab together with postdoc Fang Xin Zhou. And here, the idea, we got the inspiration from these transparent woods, where you would take a wood wafer, delignify it, and then fill in an index matching polymer. However, we wanted to do a bit simpler process, so no need to use wood as a starting material, and we started from pectin instead. Pectin is great because you can also source it from bio-waste. For instance, a lot of fruit peel waste would contain pectin that can then be extracted. So what we did here was that we started from pectin solution, and then by changing the freezing strategies, we then could get either this type of random morphologies or highly unaligned anisotropic morphologies. This here could then, you can imagine it resembles a little bit of the structure of a delignified wood. So we took those templates, and then we filled in or impregnated it with PMMA, and we got into a composite that actually looks a little bit like transparent wood. What's maybe the most noteworthy thing is that it's transparent over all the critical wavelengths that we want for our photonic devices. And in addition, by using pectin, we could get some added benefits. So here are the optical characterizations of these composites. So I'm not going to walk you through all of this, but I want to highlight a few things. So first of all, this haze component is the percentage of the transmittance that goes towards diffusive transmittance, so helps us collect more light. And here in these composite films that we had over 80% of total transmittance and approximately 50% of diffusive transmittance. So the research is still ongoing, but we believe that this might be quite a good ratio for this type of translucent films. Another additional benefit that now comes from applying pectin is that pectin has quite a nice absorption in UVA and UVB regions. So if we think about UVA blocking capacity and UVB blocking capacity of these films, especially at the UVA region, we can reach much higher UVA blocking as compared to simple glass device or simple PMMA here. So this is now one of the examples where if we take a plant-based polysaccharide, we can actually reach added benefits over the advantage of being sustainable and using a biosourced or bio-waste-sourced material. Okay, so this is a bit about the future. So, of course, the next step is to use this type of transparent pectin composite templates as supports for solar cells. And here, maybe this added benefit of the UVA blocking property can be very useful, since it's well known that, for instance, for perovskite solar cells and dye-sensitized solar cells, UV irradiation is one of the really major causes for cell degradation. So if we thus have this type of added on substrate layers on top, maybe that can also help to improve the longevity of these solar cells. And of course, the other question that we're then asking is, what other parts of this type of layered sandwich devices can be potentially built out of plant-based polysaccharides? Okay, the next part of my talk is the part where I'm going to argue that by using, again, plant-based polysaccharides, this time cellulose, can help us to build more durable, flexible electronic devices. My first example of an electronic device is an optoelectronic dye-sensitized solar cell. And now this goes a bit back in my research history to my postdoc years, when we were developing this type of new electrolyte filling concept together with Kati Miettunen, who is nowadays a professor at University of Turku. So here you can see a conventional way of building a dye-sensitized solar cell. So the idea is that you take all of your dry components, sandwich them together, and as a very last step, you use these electrolyte filling holes here, and then with the help of the capillary action, the electrolyte goes into the cell. What we did instead was that we actually screen printed cellulose nanofibrils on top of the counter electrode. We freeze-dried it, and then we got these type of sponges that are pictured here. And these sponges could then act as electrolyte supports. So you can just drop a droplet of electrolyte, and it spreads really nicely on the cellulose film. So a few benefits that this strategy can achieve. First of all, we can eliminate one very common pathway for electrolyte leakage, since we don't need to use this type of holes on the counter electrode. But also, we can at the same time eliminate one common pathway for impurities to get into the solar cell. And thus, we can argue that this can again help to improve the lifetime of the device a little bit. And a great advantage, again, was that this same strategy of using cellulose nanofibril printed cryogel type of thingies. One great advantage here is that you can also apply it on flexible conductive substrate, as is done here on a typical ITO PET substrate, and then you could build flexible solar cells based on this. All right, a totally different type of electronic device. So now we talk about energy storage in forms of supercaps. So this is a great FinCERES project that was collaborative work between my group, Orlando's group, group of Tanja Kallio and Eero Kontturi. And the work that I'm going to talk today is mainly done by our talented grad student, Yazan, who is also here. So please also talk to Yazan about this project. So as I mentioned, this is again an electrolyte design thing. And again, for supercaps, conventionally, in certain type of supercaps, electrolytes tend to be liquid. But if we move towards gel electrolytes, we can achieve benefits of compactness and flexibility. And once again, a certain advantage over leakages. So if you think that you have a small crack here, if your electrolyte is a really thick gel, so then there is less leak of the electrolyte, and potentially the supercap lifetime can be improved. So what we did in this project was that a supercap designed based on bio-waste was realized. So for the electrode materials, they started from animal slaughtery waste. So animal bones were pyrolyzed at 800 degrees centigrade, and porous carbon was formed. Now, at the same time, for the electrolyte, we started from brewer's spent grain, so brewery residues, out of which cellulose nanocrystals were extracted, and then these cellulose nanocrystals were physically cross-linked with the help of aluminum nitrate. This resulted in a very nice ionically conductive and compact gel that could then be compressed between these porous carbon electrodes. Okay, it's a long process with a lot of electrochemistry involved, but I'm going to cut some corners straight and just highlight one of the final results. So what was great here is that if you bend these supercapacitors to 90 degrees, you can see here that almost doesn't have any impact of the performance of the device. So they are quite highly bendable. And also here, I know the contrast is not the best, but you can see here how well you can manipulate these gels, so you can really twist and roll them, and they help hold together very well. But yeah, if you're more interested in this project, please go to the poster of Yazan. I'm sure he will be happy to answer all your detailed electrochemistry questions there. Then moving to the third part of my talk, which is about construction industry, which is also in a deep need of a green transition. And here we want to argue that we can maybe aid this green transition by designing novel type of acoustic insulator materials. This can be now approached like motivation-wise from two different angles. So first of all, there is the regulatory angle, which is all the time tightening and tightening. In my opinion, not fast enough, but it's good that it's tightening. So we have these goals like carbon neutral Finland by 2035 or carbon neutral European Union by 2050. And if we're about to reach these goals, what we need to do is to design carbon neutral or carbon negative functional materials. So that's the other angle. The other angle is that this is a very big industry. Acoustic insulator market is multi-billion market already at the moment. So if we are able to replace the existing acoustic insulators with something bio-based, there is a huge market to tap into. So the conventional building acoustic insulators are mainly this type of glass wool, mineral wools, and rock wools, which are far from sustainable as materials. But when you look at their structure, so here is a scanning electron microscopy image of rock wool. So you can see that it's pretty much just a network with a lot of air pores and voids inside. So this gives you a hint that this type of sound dampening properties probably stem from just having a lot of air material interfaces and interaction of the sound wave at those interfaces. This is good news for us because as materials designers, it's quite easy for us to design different type of porous networks. And what we started from was this type of bio-waste sourced acoustic insulators. And we tried 3 different type of bio-wastes, out of which kale stems turned out to be the best. And what we actually did was that we took real kale from the garden, ate the leaves, and then ground the stem into very small, and then applied this type of simplified CNC extraction protocols on this powder. We then got CNCs out of that, but because it was a very simplified process, also some lignin and some other residues was left into the suspension, but we didn't let that to disturb us, and we just freeze-dried those gels, and what we got was something that looked like this. Okay, doesn't look exactly like rock wool that is pictured here, but when we were optimizing the concentration of the CNCs in the initial solution, we were already able to find out a concentration at which the absorption coefficient, so the sound insulation properties, were actually better than for rock wool that we were benchmarking against. An interesting question then is that if you start from the other angle, so actually designing different structure and trying to understand what would be the optimal structure. So it's a very intriguing question because if you think about different mechanisms that convert heat or sound into heat, there is at least 3 different type of mechanisms, and all of them can come to play in this type of porous plant-based polysaccharide materials. And another intriguing fact is that it's not actually yet well known that how to optimize the interplay between these 3 different mechanisms. So what we've then been trying to do is to just develop libraries of varying polysaccharide morphologies. And for this task, again, pectin turned out to be quite handy for us. So what we found out was that if we cross-link a pectin solution with sodium chloride, we can actually quite easily tune the pore density of these porous cryogels. And it's nice since we have this continuous decrease of pore density, and then that again reflects on their sound absorption properties. So with the lowest pore density, we actually had the best sound absorption over the frequency range that we studied. And once again, if you compare it to the turquoise line, which is the glass pool, so you can see that with pectin, we actually get better sound absorption over the whole studied frequency range. Good. So those were a few words of what plant-based polysaccharides probably have to give for construction industry. So then in the last part of my talk, I'm just going to give you some insights about one particular topic that my group is working on, and it's textiles. And if you think about, for instance, how much textile waste is produced globally annually, which to my understanding is something like 92 million tons. So this, in addition to the construction industry, is something where we really, really can make a difference by changing into more sustainable materials. So what my group is doing is that we try to make different type of environmentally responsive textiles, so textiles that would change their properties or shape when there is an external stimulus, such as heat. And we are also doing quite some yarn development, but since that's the part of the work that is still ongoing, so today I'm going to talk about the other part, which is designing these type of modular textile structures that can react to the environment in an easy way. So this is work of a very talented future PhD student, Mithila Mohan, and she's doing different type of weaving patterns, and her task has been to try to optimize how these type of small textile actuators should be placed into the textile architecture so that the transformation of the textile when it's exposed to heat becomes as amplified as possible. And here are a few examples of those textiles. So they are flat in their first stages, and when they get exposed to heat, so then they curl into different type of shapes and forms. And here is another one of them. And now here is one of our latest achievements. So we were able to do this type of a textile that when you place it just under heat, so it kind of produces this type of quite large amplitude accordion type of motion. And well, of course, the next step is to try to replace the yarn materials with our novel yarns. That would be more sustainable. But what we envision that these type of responsive textiles can already do is that, well, first of all, if you think about the indoor acoustics, if you have something that changes its shape, maybe we can continuously adapt or tune the indoor acoustics. And the other part, which is maybe a bit more in the future, is that if we attach different type of reflective components on these, we can make this type of climate adaptive curtains. So if we want to control the amount of heat that is coming into the building, we can do it with the help of this type of adaptive curtains that can either let more light or let less light into the building. So this could then hopefully in the future contribute towards this concept of climate adaptive buildings. Okay, so I guess it's time to wrap up since we want to go for the lunch. But sort of as my wrap-up slide, I want to raise some discussion about sourcing of these materials, because the point that I hope that I've been able to make is that if we choose our polysaccharides right, we can really bring added benefits to the functional materials that we design. Now, where we get these materials from is a big question, and in my group, we've been looking into different type of bio-waste sources that could be used. And again, we started this project by mapping out available waste biomasses globally. And as you can see in this table, at least the amounts that are there are huge. Are we able to use them well? That's, I think, a big question that I want to ask, and I want to challenge us to think about how to better make use out of them. And yeah, if you're interested more of this topic of using non-wood-based materials as the sources for nanocellulose, I would invite you to read our recent review article about this topic. Okay, I think it's time to thank you all. Especially I want to thank my great group. They do excellent work every day. And I point out here from the group picture, Yazan, who did the supercap work. So please go to talk to Yazan during the posters. Then Joyce Kashuk, who did those light management films. And then I want to point out Function. It's tricky with this. Function is here. So Function has been doing a lot of those pectine cryogel works. And then, of course, great thanks to the funders who invested their precious money into our research. And great thank you to you all for your attention.